Hello everyone. Welcome to the EasyPower Tuesday Refresher webinar series. My name is Jim Chastain. I'm an applications engineer here at EasyPower. And today we're going to, as part of our general focus in this webinar series, is to highlight areas of the EasyPower tools that may be overlooked or underemphasized in our training curriculum. And I think that's true in part with today's topic, specifically how to utilize PowerFlow and improve the results that can be obtained from your one-line drawing file. So hopefully it'll be something that benefits the audience. So our agenda today is basically to emphasize the advantages, not so much the overall operations of PowerFlow, but specifically how it can be used to improve your one-line diagram in your database, and then ultimately encourage folks to utilize to greater extent the capabilities of PowerFlow. So before we do that, we'd like to jump into a couple poll questions. Appreciate the feedback, and I would appreciate your participation. So the first question is, how often, in your opinion, should a system require or receive a PowerFlow analysis? Again, there's no liability, no obligation, strictly just for my edification, understanding the audience perspective on the topic. And not knowing is as good as anything else as far as an opinion. So I appreciate your honesty. So it looks like we're close to a quorum. Let's leave this another 5 seconds. Okay. So here's how folks have weighed in. All right. And I pause at this point because before ArcFlash came along, facility engineers, in my opinion, lived and breathed PowerFlow results. And it was something that was handled, if not on a daily basis, on a regular routine basis. And so it's interesting how things have kind of shifted with the emphasis on, and part of that is some other technology that's come into the market that perhaps is allowing a different perspective on the system without going to PowerFlow. So again, that's just my opinion. So if you're an EasyPower user, do you use unbalanced PowerFlow? This is equally interesting for a number of reasons. And 11.0, EasyPower 11.0, we released unbalanced PowerFlow, and it was a big deal, at least from an internal point of view, because it opens up a lot of improvement in the tool suite, having that capability in our code. So you'll see me use it, and hopefully you'll gain an appreciation for it. All right, so we have a quorum here. Here's how folks have weighed in. So hopefully with a dominance of people either not knowing about it or not using it, hopefully you'll gain some insight into how the advantages. And then finally, what is your focus when you do a PowerFlow or use PowerFlow? What are you trying to do? What's your focus? And again, these are not scientifically designed questions. They're just stuff I'm curious about. Okay, we're 2/3 of a way to a quorum. Let's leave this another 10 seconds. We do appreciate everyone attending today. You will receive a attendance certificate for the time you've attended, and you're welcome to ask questions as we go. So here's how folks have responded to that question. Excellent. And I appreciate that very much. Okay, some of the other things I'm going to be talking about, as I mentioned, I'm not going to be getting so much into the basics of the PowerFlow, but emphasizing some of the capabilities of the tool along the way that actually have migrated and we haven't talked that much about in the release of 11.0. So PowerFlow is the solution to a steady state condition, basically at quiescence or a resting point for current, voltage, and then power flow in a system for that particular condition. And as I mentioned, as we get into this, I'm going to be using EasyPower quite a bit, and I want to make sure you're kind of paying attention to what I'm looking at, because sometimes the little cursor moves pretty fast. But essentially, we have the ability to control the unit display for the voltages in either per unit or in kilovolts, and then also included the power angle. The power angle is the difference between the reference point, which is utility or the power connection, and the power angle at the bus in question. Then when we're looking at utilities, generators, and loads, we have the ability of displaying kilowatts and kilovars, or kilowatts and power factor. And then branch flows are in kilowatts and kilovars or amps. And then transformers are in kilovolts. And what you'll see is I will continually reference these icons in the top left, which can turn on and off each of these elements in the one line. And then on the second row, we have the ability to look at overloads and voltage violations. So as we get into this, that's what we're going to be kind of actuating or emphasizing. So I have a series of examples to demonstrate cable data error corrections, load scaling to match actual load scaling, optimization of voltage by adjusting or recommending adjustments for the transformer taps, then some examples of power factor correction, or at least indications where it's needed, and then locate elements that are incorrectly modeled, all of which can improve your utilization of the database that you construct for ArcFlash. So we're going to open a one line here that I've got set up for today's meeting. And it turns out it's a pretty large file, and there's some features that I want to make sure you're aware of. So if we open up any file and right click in an open area, I can go to options. And normally under the system tab, normally or the default setting for PowerFlow settings is balanced, which has been the case for a couple decades. With the release of 11.0, we also have the ability to do unbalanced, which allows us to do single phase loads and the impact on the system, and then does additional error correction or error identification, which is useful when you're doing debugging your system. While I'm here, although we don't talk about it, any frequency can be used to do my power flow and short circuit analysis and even harmonics. And this has an impact on sometimes the impedance and certainly the reactive results. But for arc flash, the arc flash model is only good for 60 cycles or 50 cycles. So that's another thing to beware. This affects the whole operation of the system. I can't do part of the system in 60 hertz and then the other part in 50 hertz. So now I've got set up for unbalanced at 60 hertz. And we're going to go into our one line. Now, one of the features I'm going to be using fairly often is, and it's very useful in a large system like this, it's called name views. And it resides under my easy control. I'm going to stake it out here, pin it out. Down at the bottom is name views. And the way this is set up is I've zoomed and panned and then saved those settings on this list. So for instance, if I want to refer to the utility section of this one line frequently, I may go up and save this as a name view and say utility. And now as I go back and forth in my list, I can refer to that point relatively quickly. Now, the point I want to make is when I go to PowerFlow, one of the things that results is an error list. And I can ignore the warnings and continue, or I can view the report. And so in this case, it tells me there's a cable that has no neutral wire for connections between three-phase, four-wire buses. It looks like it's C12-2. So let's go back to my one line and go to database edit. Well, actually, I can fix it from where I was. So let's try that again. PowerFlow. Edit. And so what this is telling me is in the data block for this cable, if I go to neutral, I don't have any neutral cable indicated. So I need to go back to my one line diagram and fix it. So CT12-2. Let's go ahead and close this report. Let's go to database edit. And find cable CT12-2. And again, we're looking for the neutral wire situation. So now as I'm looking at the specification tab, I can see this model was created prior to having auto-calculate as part of the data log or data box. So I'm going to make sure we auto-calculate it. I'm going to do a neutral, same as the phase. And the phase in this case is a single conductor 500 kcmil. So now if I do that, I go back to my database edit, PowerFlow, solve, I get a solution. So that gives us some indications of what we can look at. And the red flags are the function that are requested by the second row of icons up here in the top left. So I'm just going to cycle through these. You can see which ones turn on and off as we click on the icon. So voltage on the bus. So I'm looking right here at this on the oblique, and it looks like it's per unit, and the phase angle is minus 65 degrees. For my utility, let's go back and look at the utility. I can turn it off and on. It's showing 19.6 megavar and 11.4, excuse me, megawatts 19.06, and then megavar 11.40. If I right click in an open area and look at the PowerFlow options, it gives me the ability to control on the one line output my display units. And for generators and loads, I'm currently showing the megawatts and megavars, but I can just as easily show the megavar, mega VA and the power factor, which we will be using here shortly. Bus units, as I mentioned, are in per unit or voltage, branch flows in megawatts and megavars or in current. So we'll come back and utilize that in a second. Okay, so we can also show the loads information, which is megawatts and megavars. We can show the branch flow, which is inline, and again, it's megawatts in the first number, and then in the parentheses we got megavars, and then transformer taps down here in my transformer. So I have 67.275 and 13.8 kV on this left. Okay, so let's look for some of the errors. And so I've highlighted in this particular case this overloaded cable that looks like it's 2,000% out of whack. The data block shows it's rated for 10 amps, but we're trying to shove 220 amps through the pipe in normal operations. Well, now this is something that wasn't caught during short circuit analysis. And so this clearly is an issue. And if I go back to database edit and double click on this icon, I can see, sure enough, it was just a mistake. And in fact, this should be 350 kcmil if I check my notes. So by checking 350 kcmil and auto calculate, now I'm going back to PowerFlow. Now it's not going to be an overload indicated as such. Now, one of the reports, I'm going to touch on this here in a minute, but one of the reports that I can show if I go up to PF reports is voltage violations and line overloads. So this will give me a list if I want to go down the list and fix them, which we're not going to do now, but this is part of the report generation. Okay, and that's how I would fix sizing. Now another thing I'm going to go to the motor bank. Another way to improve my alignment between my simulated database and the actual physical system is by matching what the loads are, the load magnitudes are, versus the what the motors are running in the system. So for instance, if I knew this bank of motors normally runs at 85%, I can select all of them and scale in mass motor data to be 85. It looks like I've already got it set up. 85%. Now I can make this anything. Then to be more accurate, if I had data logging included, I could I could set these individually, in which case I'd see a better result as far as my voltage and current simulation. So looking at this same block, if I look at the voltage overloads, voltage violations, I have the flag set at plus and minus 5%. 5%. So here we have a per unit of 0.91, which is outside the band, and it looks like it's just slightly less outside that band on T6 secondary. Now there's multiple ways to increase the voltage, and I'm not going to start justifying one direction or another. It depends on your system, but I like to begin with making sure I've got the taps identified for the transformers, in this case, that are just upstream of those buses. So in this case, I can see I have set up 13.8 and 480, which are default on both of these transformers. The tool will give me the ability to optimize or recommend taps based upon the loading and the downstream loads if we set it up in the data block. Each transformer data block has a tab called LTC. Now, even though this transformer doesn't have a load tap changer, if it did, the tool would recommend what the tap settings should be to give us optimum output. So for starters, if I look at my notes, I can see this should have been a 1500 kVA transformer. So let's go back and change that. And then secondarily, my load tap changer, let's say adjust the primary and base it on the output and lock in the output of the secondary. So I'm going to do the same thing on the other one. And it's telling me that I need to recalculate my overload. So that's cool. And let's go to this side and set up. And then after I get the recommendation and I've kind of done with optimizing, I can go back and set the fixed tap settings for whatever recommendation I want to go with. All right, so we've got a tap setting there for load tap changer. Now I'm going to go back into PowerFlow, solve. Now I'm up here on the icons for overloads and voltage violations, and we no longer have voltage violations, at least on the output of these two transformers. And that's because it's recommending the tap to be 12.765 on the primary to get us 480 on the output, and 13.1 on this one to get the output locked into 480. So let's say for now, I'm happy with that, and we can go on about our business. Now we keep talking about power factor. Power factor is placing, or one way to deal with it is to place capacitance near the load and take up some of the slack for the reactive current that's flowing to keep that load rotating. So in this case, if we go to power factor, I've got a zoom in or a named view set up for my utility that includes these two power factor capacitors that we don't have selected. So and we're not really having too bad of luck with 0.992 for this bus, and this one's 0.992 as well as far as the voltage. So I'm going to go up and change my display on the utility to power factor to be MVA and power factor my one-line output. So that's generations and loads, MVA and power factor. And we can say with the motor loads that we have, we've got a 0.865 power factor without those capacitors included. So let's turn those capacitors on. Now another feature that's part of the PowerFlow module is the ability we call Smart Breaker. I can just double click on the breaker and it will activate and then recalculate the PowerFlow solution. So with that capacitor in line, we improve the power factor a little bit. And with this other one, which is this breaker here, we bring it up into a range that's much more suitable. And what we see as we exercise these is that the upstream reactive current changes a little bit. In this case, it's 4.865 or 855 megavar, and it drops by 500 kilovar. And what it's doing is offsetting that much reactive current into these loads that are on the same bus. And if we exercise that, you can see it change slightly. So this is sustained, but it doesn't have to go through, the reactive current doesn't have to go through the transformer. That's the whole benefit of power factor correction on the bus. It slightly brought up the voltage, so that's a good sign, and it reduced the losses that would be experienced because of that reactive power now is no longer being drawn from the utility. Now I can do that. Power factor correction is most useful if it's on the bus, closest to the bus where the reactive motors are drawing current. So this might not be the only place. It might even not be the best place to put power factor correction, but it's good for this example. Okay, the next thing I want to show is incorrectly modeled devices. If I close this breaker, so this PowerFlow is different from short circuit, and we can go in and fault a single bus in short circuit and see what the short circuit current is and the arc flash is. Whereas in PowerFlow, it's a reiterative process that considers all the elements and their effect on each other. And so if I close this breaker that's over here on S1, the switch, I see I get an error. One of the error solving techniques is to isolate all the breakers on that bus and then close them one at a time until you find the one that's busted. So that's why I know this one's, everything's working as long as that breaker's open or that switch is open. If I go down here and see what else is going on, I can see I have a load, I have a rectifier. So I'm going to, and the other switch I have down here is this load switch. So I'm going to isolate that and see if that helps things. So if I close this switch, now the solution, the PowerFlow solution is good. And I see a small amount of current power flow and reactive power flow as long as this motor is offline. So it brings to mind what's wrong with this motor. Well, if we go back to our database, edit, let's go ahead and save everything we've done so far. We see that this is roughly, if I look at my rectifier, 500 volts and 350 amps. So it's 175, 180 kilowatt rectifier. We have 1,000 kilowatt motor load. So I can see my problem real quick is I slipped a digit when I was building up the dialog box for this motor. So if I go back and check my notes, sure enough, it's only 100 not 1,000 kilowatt, and it's set up for 100% scale factor, so let's go ahead and leave it there. Go back to PowerFlow and solve. And sure enough, now we have a solution. And if I close the breaker, I'm drawing 100, and this is just the real power because it's a DC circuit. 110 watts, 110 kilowatts, and AC, reactive power, and real power. So I was able to identify the problem there. Okay. I did want to touch on impact motor start because, in fact, this question just came in over the weekend, is that what's the worst case that will happen to my system if I start a motor while it's, and it instantly places that load across the line. So, and I'm not going to talk about voltage drop or SCADA input, and we touched on power factor correction already. So the point is, motor start is another handy dandy capability. For instance, if I have, I'm in my normal operations, I've got PowerFlow solved, I've got large motors here. What happens if I start these two motors at the same time? Well, to do that, I have to go in and condition the dialog box while I'm in PowerFlow to start the motor on command. And at this point, we're going to start it at 0 load and do the same thing over here. There's any number of motors I can start at the same time, or I can start them individually. But we're going to start these two at the same time. And what we're trying to see is what the impact is on the rest of the system. Obviously, somewhere along the way, we need to deal with these other cables, but that's beyond the scope of this discussion. Okay, so now we solve the equations with those two motors offline, as indicated by the loading and power factor. And then we start the motors. We can see it pulls this bus down to a 0.82 per unit voltage, as well as there, as well as the draw on the transformer bumps it up to 144% capacity during that instant that it's across the line and while the motors are not moving. But the impedance of the transformer is good enough that it doesn't affect buses in the rest of the system. So if we go back and replot that, I can see it's pulling this bus down to a 0.9 something or another, 0.99, but that's not enough to drop its control system offline. So this technique is quite literally to see if we have flicker issues or sag issues based upon large motors coming online. And at least for this case, they're relatively benign to the rest of my system. I just think that's pretty cool. Okay, so it looks like we're running out of time. Yeah, so one of the other applications, and this is not a database application improvement, but it's one of improving my ability to apply or make sure I'm utilizing infrared scanning, and that is to identify hotspots, overloads in my operations, so that when I do have a scan to do a thermal scan system, I make sure I identify it at full power versus having it offline or reduced power, which may not show the same result that we're seeing in PowerFlow. Probably didn't explain that, but ask if you got a question. Okay, then what if, again, the PowerFlow capabilities can be used to look at what happens when we try to change capacity or move loads around to different parts of the system. The ability to improve tap settings or adjust peak load conditions. The ability to say what if's going to happen if we have code generation online. And then the impact of firing off emergency generators with certain systems online. So anyway, PowerFlow is extremely useful in debugging my one line and making it more accurate. And then in operational, it gives us the ability to do some troubleshooting and what if scenarios as we're trying to improve the capabilities of our system. So what we try to do is show the benefits of PowerFlow when modeling, and then how to optimize in a day-to-day operation, and then consider answering questions before we have to make decisions on modifications in the plan. So that covers what we wanted to do today. Appreciate your attendance. I do want to mention that we're having instructor-led training here online later this month, and then in-person training here locally at Portland in July. We're listing our Flash workshops at no cost every month, and they're on the website under resources and events. So make sure you track the webinars in the newsletter, and if you got technical questions with the tools, feel free to contact support at easypower.com. Thank you all for attending and have a good day.